a deal. The reason that we were interested in this topic, and the reason I'm glad to see so much industry interest in this topic, is that rouge in pharmaceutical and biopharmaceutical manufacturing it's definitely a hot topic issue. It's a current issue, and one that some manufacturers might have some difficulty in strategizing a response to, or remediation. So what we hope to do today is to kind of lay the groundwork, so kind of build a foundation of an understanding of what rouge is and how we typically address the issue. So we're going to talk a little about kind of the characteristics of stainless steel, the different types of rouge and how it's formed, and then we've got some strategies on remediation and some case studies. So with that, I'm going to turn it over to Beth and Amanda to kind of kick things off. Beth?
Good morning or good afternoon, everyone. I hope you're excited to learn a little bit about stainless steel and rouge and passivation and what it is. I'm normally well, not normally, but I'm a biochemist by education, and I'm a parenteral drug manufacturer by trade. I've been at Stairs for 3 years, and I hope that I can disseminate some of the information that I've learned about rouge, how to remediate rouge, the importance of cleaning in your derouging process, and what is passivation. So to start, for the agenda, first of all, we're going to talk about what is stainless steel. Is it really stainless? The origins of it, what it's comprised of. Then we're going to talk about some of the natures, types, causes of rouge, discuss what is passivation and some of the guidelines and literature out there to talk about what is passivation, stainless steel and corrosion. We're going to talk about some of the solubility of the iron oxides, derouging, and some issues to consider in industry. And then part 2, we're going to go over some case studies, and then of course we'll have our question and answer. So, stainless steel. We all know it's not really stainless, although we would like it to be. It was originally developed in the early 1900s. So in case any of the listeners ever go on Jeopardy, here's some fun facts for you. It was originally worked on in the early 1820s by some Frenchmen, one of whom's name I cannot pronounce, but I will do my best, Berthier. And he was the first to alloy chromium with iron. Then who really brought it to industry and who really gets the credit for it is a man named, he was a metallurgist named Harry Beerley in 1913. And he is generally accredited with the invention of stainless steel. It was kind of by accident how he discovered it. He was actually researching how to improve the stainless steel or the actual carbon steel inside of a gun barrel and how to make it more resistant to the erosion that occurs when the heat on the internal surfaces of the gun barrels, as I guess the bullet would go through the gun barrel. So in his research, what he would do, he would polish and etch these metallic surfaces with the dilute solution of nitric acid and alcohols. And of course, this worked well for carbon steels, but then when he started working on the steels that had the chromium alloy, he found that they were rustless. And he originally called these materials rustless steels, but then of course a good marketing person came along and told him no, he should be calling them stainless steels, and much like the Facebook turned into Facebook, we now have stainless steel. He was originally from Sheffield, England. They were an area where they had a lot of cutlery, and he thought it was a good invention for the cutlery industry. So because of this man, we now have great stainless steel knives that don't rust, and we have, of course, our nice tanks that we all use in industry. So what makes it stainless is actually the addition of iron alloys with a minimum of 10.5% chromium. Other metals are added to enhance the structure of these, some of which are nickel, molybdenum, titanium, copper. The addition of molybdenum is really essential for the stainless steel attributes of what gives stainless steel its stainless steel attributes. Okay, on this next side we have some basic compositions of stainless steel of 304, 304L, 316, 316L. For those who don't know, the L means that it's actually lower carbon content. And what this does is it minimizes the precipitation of chromium carbide ions caused by high temperatures when they're welding. So the original stainless steel, you have the composition down here, and then there's, of course, a picture of Harry Brewerly. All right, so the nature of rouge. What is it? It's a corrosion product of stainless steel. It's comprised of predominantly various forms of iron oxides. Where do you find it? You find it in water systems, find it in processing equipment, find it in high salt solutions such as buffer tanks. And some will wipe off easily, others can be tenacious, others can be brown to black. When troubleshooting rouge, the questions that I would really ask if somebody called up and said that they had a rouge problem is the first thing that you would want to know is, well, what color is it? Can it be wiped off easily? Where is it located? Is there a pump involved? Things like that when you're trying to troubleshoot it.
Yeah, I think that's a great point, Beth, and something that we're going to highlight as she goes into the different types of rouge is that, you know, rouge is not rouge is not rouge, and there are a lot of different types, and depending on the type and some of the characteristics of the rouge that you're seeing, that's going to dictate more or less our strategy in addressing it and remediating it.
Good point. So type 1 rouge, what is it? It's oxidized metal particles generated from external sources by erosion or cavitation of pump surfaces. This is important because pumps are prime suspects in an otherwise clean system. The two mechanisms involved appear to be cavitation, or maybe because of impeller velocity. Type 1 rouge can be easier to remove. It can be wiped off, but of course we know if we have a pipe, you can't get in there and actually wipe off the pipe, so that's where you'd want to have some sort of chemical treatment, some sort of mechanical action to remove the rouge from the interior of the pipe surfaces. Type 2 rouge. This is rouge formed in situ oxidation of stainless steel. It's tightly adhered, and you might have underlying damage. Type 2 rouge, continued. It can occur when you have chlorides or other halides present. Halides are, of course, for the second column from the right on the periodic table, so in case anybody's wondering what halides are, be fluorine, chlorine, bromine. It's corrosion-driven and forms on the surface, and it occurs in a two-stage reaction. The reaction is up here in case anybody wants to refer to it later. It should be coming up. There we go. The first stage of the reaction is the dissolution of the chromium oxide layer, and then the second stage is the oxidation of the iron in the substrate material. And interestingly, the reaction is pretty self-precipitating or self-perpetuating by the chloride reacting with the chromium to form hypochlorous acid as a byproduct, which then oxidizes the iron and forms more chloride. So this is kind of a tougher type of rouge, and it really can self-precipitate. Type 3 rouge, our favorite. Type 3 rouge, well, not our favorite, but it was always fun to try to deal with. And hang on a minute. All right, sorry, I lost my my slide. So it's generally becoming a little bit more accepted in industry when this occurs. Before, like if you had a centrifuge and maybe it was sipped, and then the quality person came in and looked at it, they might see the black rouge and raise an issue. But I think if they're educated from the beginning and you write this into your procedures, it generally is becoming more accepted. It's this black oxide rouge that's generated from high temperature steam, so it can happen in SIP systems and WIFI systems. That actually forms this black layer is non-reactive, and it behaves like a passive layer actually. It will grow to a limiting thickness that prevents further diffusion of oxygen, and it typically On electropolished stainless steels, it can be like a glossy black, like what's on the picture that's shown right now, or it can be a powdery type of a black residue. Type 3 rouge, the general approach is not to remove. It's non-reactive, so it works in the same way as this passive layer. And this type of rouge is the temperature reaction product of steam with the. So what is this cause of rouge? We discussed previously, it's found in highly corrosive environments. So what are those environments? You could have distilled water and steam, chlorides, so in a buffer system where there's high salt, if you're making some sort of buffer with a 2 molar or 1 molar salt solution, it can be found in those types of tanks. High temperature, stress, or erosion. You could have non-stainless steel components. I know sometimes you might have a system where you might have use a softer metal, say around threaded parts, so that the metals don't gall. This could be a place where you'd have non-stainless steel components touching stainless steel components and non-compatible components causing rouge. You could have improper surface conditions, so improper welding, surface defects, scratches, and then of course it can also come from inadequate cleaning and inadequate passivation. So what's the result of that? When you do have rouge and it gets to be where it's seen on the surface, it can increase the surface roughness. And what this leads to is a reduced cleanability and sanitation, because as that rouge gets in there, it makes that surface, instead of a nice smooth surface, you have little valleys, peaks and valleys, where the actual residue can adhere to, and then microorganisms can adhere to that, and then the microorganisms can cause microbial excursions, of course, and then these can actually, their byproducts, can actually cause further pitting and rouging. So that can lead to product contamination, and of course, what we all don't like is it could reduce the equipment life. So what's passivation? It's the chromium-enriched passive layer in the presence of oxygen. This can be formed either spontaneously, as it happens, it's a spontaneous reaction with the air and the environment, or it can be chemical passivation that works by dissolving the free oxygen, by dissolving the free iron in the surface with treatment of an acid. So that's what this picture depicts, is it's the inside of a pipe, and so you have the chromium oxide layer with the iron going in the solution. Chromium atoms and their oxides are actually similar size, so they tend to pack neatly together on the surface, forming that stable layer of only a few atoms thick. But the iron atoms are actually much smaller than its oxide, so that oxide will form a loose, rather than that tightly packed layer that tends to flake away. So that's why that rouge, that iron oxide layer tends to be flaky and less tightly adhered. You may be asking, why do I have an iron of the iron pillar of Delhi depicted on this slide? And this is just to kind of drive home one of the points that I want to make in this presentation, that a clean surface is actually critical for this formation of the oxide layer. Because if you don't have contact with air, you're not going to passivate your surface. So what the iron pillar is, it's the oldest example of alloyed iron. This, the passive layer that formed on this iron pillar, it actually isn't due to chromium oxide like what we have in our stainless steel, but it's due to the phosphorus content that formed when the iron oxides and phosphate, rather than the damage formed, rather than the rust that could form and lead to pitting and structural damage. This pillar was built, just to say where it came from, it was built in honor of the Hindu god in memory of King Chandragupta. So again, if you go on Jeopardy, you have the answer to that. But the actual, what I want to point out here, as we can click ahead a little, is that this clean surface is critical to the formation of the film. Because this pillar, what happens is there's a custom, because it's considered good luck that if you can stand with your back to the pillar and then reach around and make your hands meet behind it, it's good luck. So the practice led to significant wear and discoloration on the lower portion of the pillar. So click ahead. So if you can see that that lower portion has been discolored and kind of what I would call rouged because of people putting their kind of dirty hands on the pillar and then not having a clean surface, and then it led to rouge formation. So there's an example in real life of how that happens. All right. So passivation. The chemical methods that can be used to enhance this passive layer, you can use nitric acid, phosphoric acid, citric acid, or other proprietary coolant formulations that are typically used. Nitric acid and citric acid are ASTM recognized. There's ASTM A38006 and ASTM A96705. Those are the ones that recommend the nitric and the citric, and then the ASME BPE actually mentions phosphoric acid. The references for the passivation are found here. So again, you have the ASME BPE 2009, non-mandatory Appendix E, passivation procedure qualification. And what this reference, what it describes is, it defines a method for qualifying passivation process. It has process descriptions, variables, specs with acceptance criteria, and it's actually intended for a passivation provider. So it provides a mean to qualify someone else if they come into your facility and say that they're passivating your equipment. It gives you a quantitative acceptance criteria and detailed procedures. So it has an appendix that provides info on passivation procedures and actual methods to test the surface. And again, like I said before, it mentions phosphoric acid, it has acceptance criteria, and it also has an actual specification at certain depths for your ratio of chromium to iron. Okay, and the ASTM 380, it's a standard practice for cleaning, descaling, passivation, stainless steel parts, equipment, and systems. What this standard does is it describes how to clean, descale, and passivate, just like the title says, stainless steel, but it also gives you methodologies to inspect. And in this reference, it only talks about gross and precision inspection techniques, where the ASME actually gives you some information on electrochemical pins and some other methods, which we'll talk about later on. The ASTM designation A96705 is the standard specification for chemical passivation treatments for stainless steel parts. And what this does is it provides detailed information on passivation treatment procedures with respect to TACT. So we're all familiar with TACT with our cleaning procedures, our time, our action, our chemistry, our temperature. And it gives the acceptance criteria for the confirmation of effectiveness. So I'll read you right out of the ASTM methodology what is passivation. According to ASTM A380, passivation is the removal of exogenous iron or iron compounds of stainless steel by means of chemical dissolution, most typically by treatment with an acid solution that will remove surface contamination, and this is most important, but will not significantly affect the stainless steel itself. I think it's important just to get everybody on the same page of what is passivation. So the ASME BPE 2009 non-mandatory appendix, like I mentioned before, it mentions the phosphoric acid, but it also has the depth and specifications for your chromium levels at specific depths. So according to this, the chromium iron ratio should be greater than 1 at 15 angstroms, so you actually have quantitative specifications that you could provide either your provider or you can use it as a check. And again, this is done, this isn't an easy way to measure your surface because you actually have to go down and look at it with the XPS, but it gives you a specification, and this is typically done on sacrificial coupons. Okay. This is a part of the ASME BPE document where it lists specific methods for passivation. So I just wanted to provide an example of that. It talks about nitric acid, the phosphoric acid, citric acid, and it just tells you how to passivate. It doesn't go into great detail. You have to get that from your ASTM A380 method. But it does list a nice comprehensive text matrix for evaluation of your passivated surfaces. So it divides them up into gross inspection, precision inspection methods, electrochemical field inspection methods, and surface chemical analysis. So your gross inspection methods would be your water immersion testing and drying, high humidity, and salt spray. These are not all inclusive. I'm just hitting the top, you know, the top ones that are normally used. Like I said, this is a gross inspection. It has pros and cons, of course, with it. So the pro, the con, well, let's start with the con. It would be that these are non-quantitative. So they are, you're not going to be able to tell how passive your surface is and to what depth. And I guess the pro would be that you can cover a large surface. But I don't know about the listeners, but I know I could never take a big buffer tank and dunk it into a tank of high salt or expose it to high humidity. It's just not practical. But these are the methods that are out there right now. As far as precision inspection methods, like I said, this is not an all-inclusive list, but it would include methods like copper sulfate or potassium ferrocyanide, nitric acid method. These are not quantitative also, but they're very sensitive. And they tend to be very user, I guess it really depends on how familiar your user is with these tests because they can be very sensitive. Electrochemical methods out there, you can use cyclic polarization, electrochemical pen. Cyclic polarization, the problem with this is that it's a destructive test. So again, you would use a sacrificial coupon. So you would come up with a methodology, try it on a coupon, and then go to your piece of equipment and actually use it in situ. So it is destructive, but the good thing is that it provides direct measurement. Yeah, keep going. So the cyclic polarization, one thing to note about that test is that it measures the critical pitting potential. So the more positive the CPP, the more passive your stainless steel is. Your electrochemical pens and your Kozlo test, your EC pen, it's a pass-fail result. Your Kozlo test will, Amanda's going to go into a little bit more detail about that. Some of the pros with the Kozlo test is that it's a direct measurement. Some of the cons is that you can have repeatability issues, but I tend to think that it's more of an impatience issue instead of a repeatability issue because freshly passivated surfaces might take a little bit longer. And lastly, you have your surface chemical analysis where XPS or X-ray photoelectron spectroscopy would be probably the top used method for this. It provides elemental analysis of your actual elements in the composition of your metal, and it can measure down to 10 angstroms to 100 angstroms. Amanda's going to discuss the Kozlo test now since she runs it all the time in the plant, so she's going to talk about it.
Yes, the Kozlo test kit is a very easy to use field tool for just about anyone to use. It's pretty simple, but it's based off the free iron on the surface, and that can be related to can be measured with the voltage measurement, and then can be related to the passive state of the metal. So what you're going to get is an actual reading of the millivolts that it's reading, and it's going to be on a bell curve. If it's too high, it's going to be non-passive. If it's too low, it's also going to be non-passive. You want to find that right there in the middle, that passive range to get a passing result. The actual instrument is very easy to use, and it's non-destructive, as Beth said, so it's great for using in your equipment, or if you're also doing coupons. You just have to have a little bit of patience with making sure you don't try to read right as soon as you've tried to passivate the equipment. You don't want to use it on a wet surface or right after you've passivated. You could probably give it up to 24 hours to wait. The actual procedure is really simple. You just take the actual instrument and you're going to put on a nib, as they're called, that has been wetted with an acetic acid solution that's in the kit, and you're just going to gently push that onto the actual metal surface, and you're going to get the result of either a nice little bing which is going to be its passive, or a buzzer sound that it's not, and it's also going to be correlated with either a green or a red light. So, you don't have to be a genius to operate this equipment. Anyone in the plant can go ahead and do that, and it can give you immediate results as to whether or not it's passive. These are not very expensive equipment. I think they're running around $3,000 right now, so that you don't really have to, put in the amount of money you would for XPS or other testing like that. And the actual running the equipment, you just have to use a new nib every time you go to an unpassive surface, and that's generally, the upkeep is not going to be expensive. So it's really nice to have. It can be used on just about any stainless steel. Typically I do 304 or 316 with it, but it can give you, test conditions and results right away as to what is going to work and what most likely is not.
An example of how this was used to actually help a customer, this is work that the Processing Cleaner Evaluation Lab did with the customer under the direction of one of my coworkers, Paul Lapolito. And what they were doing is they were making a salt solution, or a 2 normal chloride solution phosphate buffer in a tank, and they were having trouble with maintaining the passivity of the tank. So they were wondering what conditions actually caused the tank to become passive or not passive. And so what they found by soaking, now again, these coupons that they started with, they were cleaned and then they were passivated using a solution of 5% Procons 2, which was one of our acidic cleaners at 80 degrees C for 90 minutes, and then rinsed with DI. They were tested with the Coslo to confirm that they were passive before we started. Then they were exposed to these buffers. One was soaked overnight in the buffer, and then when it was cleaned, it was passive. One was soaked over the weekend, so it was passive. When they soaked it for 72 hours, they found that it was not passive. So what they did here is they actually determined a buffer hold time condition that they could still, so if they went over the weekend, they knew that they could filter that buffer the next, like on the Monday, but if they went over a 3-day weekend, that was not acceptable. So they established a buffer hold condition. What they did to determine dirty hold time is they dried the buffer on the coupon overnight. They found it was non-passive, and when they did it for 60 minutes, they also found it was not passive. There's some other data that was generated, and they came up with the conditions that actually repassivated these parts or the tank, and found the conditions and determined a hold time. But I thought this was interesting data to show how salt solutions, how buffer conditions can impact your buffer tanks and the passivity of it, and how that Coslo was used to actually perform a lab study experiment and come up with the conditions to give you buffer hold times and dirty hold times. So this next slide shows the next PX depth profile, and since I don't have a pointer and I don't know how to get it to you, what it does is if you look at the left axis, that would be the surface of your metal. So if you just picture that as the surface, and as you move to the right, that would be the depth of your metal. So what this does is it shows the chromium-iron ratio on the surface of that metal moving down. And what we did here is we compared nitric acid, which is the ASTM gold standard. Typical use concentrations that are recommended as far as the ASTM A967 are 20 to 45% volume per volume. We use 17.5, and we compared it with our 15%. This is our CIP 100 cleaner. Oh, I'm sorry, CIP 200. Sorry, I'm thinking of cleaning. That's a latter slide. We compared it with our CIP 200, and you can see that the lines show that the chromium is similar for both chemicals. So CIP 200 compared to the gold standard of nitric. Okay. So my coworker looked like he just drew all over my next slide. So, so nitric acid. So that is the gold standard, right? And I know in the facility I worked at, whenever you mentioned bringing in nitric acid, the H&S person's hair just stood up. So, you know, there's safety advantages, or actually safety issues with nitric acid. There's advantages of using citric acid or phosphoric acid for passivation rather than nitric acid. And also there's this major advantage at the atomic level when you're using an organic acid compared to a mineral acid. Your nitric acid will attack the surface iron first, but when it diminishes that, it'll start going after other elements in the alloy. What it does is it effectively limits the depth of the final passive chrome oxide layer, as well as introducing heavy metals into your waste stream, and these are going to be classified as hazardous waste. Nitric acid, it poses a significant risk to your personnel who are working with it, and typically when these systems are derouged, you have some sort of action involved, so then you have a pressure involved, and then you heat it, so you intensify that risk. And then after you use it, careful handling is required. So it could be expensive to transport it off your site. I know in some sites they have an actual, an actual company that ports this off-site, so it could be expensive. And then in addition to being corrosive, remember that nitric acid is also an oxidizer, and so you have to have special precautions in place when you're dealing with this. Citric acid, so it works a little differently in that it actually ties up the metal ions so that they're no longer effective and they won't have a negative impact. So after stripping the metal ions from the surface, the acid forms a water-soluble complex with these metal ions, and it won't precipitate again and attack the iron or the stainless again like your mineral acids will. And then also citric acid, it's in oranges, it's in lemons, it's in citrus fruits, so it's generally regarded as safe. This slide right here depicts citric acid compared to our ProCleanse 2 and our ProCleanse 2 detergent and our CIP 200 detergent. And we did this experiment using a lab-generated rouge coupon. Amanda's going to tell you how we did that.
The lab-generated rouge coupons are typically done on 304, 316. They are put into a sodium chloride solution along with a carbon steel source. So what we're making here is a type 1 rouge that's transferring from that carbon steel to that 304, 316. The solution is aerated typically and stirred for about 7 days to get a good amount of rouge present. And then you just remove them, let them dry, and you now have your rouge coupons ready to go.
So if you can look at the slide, it shows that we used a 37% citric acid, and when compared to an acidic cleaner that has the detergent and other proprietary components in it, you actually have a better derouging. So it shows that we were able to, our derouging conditions when held constant at a 2% volume per volume dilution at 60 degrees C for 30 minutes, were actually to remove more rouge using the detergent blends than just plain citric acid alone. So how is passivation performed? So like I said at the beginning, that cleaning, 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 you want to make sure that you have that clean surface, because if you don't have the clean surface, you don't get the contact with the oxygen, and you definitely don't get the contact with your acid on that surface. So the typical process usually begins with a thorough cleaning cycle to remove your oils, your processed soils. If it's a new piece of equipment, your cutting fluids, your lubricants, anything that may be used in the actual manufacturing process. And then you want to pay attention to your 3 variables, of course, because you know the chemistry, you know you're going to use an acid, but you want to pay attention to the action, you want to pay attention to the time and the temperature and the concentration. All of these play a part in how something is derouged. The typical contact times are between 20 minutes and 2 hours. However, you may have a more tenacious rouge that requires maybe 4 to 9 hours if it's something that's not done routine. If it's a water system that maybe you crack open every 2 years, you might have to do it a little bit longer, so you kind of have to weigh that. And then the 20 minutes you might want to consider it more as a routine maintenance. a suggested approach for derouging. Here we have a typical time versus iron concentration graph that shows your initial iron increase. So if you start with a concentration of 10%, you would measure the iron until you plateau, and then you could add either more acid and let it go again until you plateau again, or you can just start with a higher concentration, say 20%, and just go right on up and avoid that secondary plateau.
And one of the easy ways to determine if you are hitting that plateau or if you are still removing iron from the surface is using the Hawk test kit, which can be used again in the field. It's very simple, a little bit more than the Coslo, but it is a simple approach that can be done by the person who is working on the derouging. Basically what you would do is you would remove an amount of solution from whatever it is you're derouging, check the pH. You want to adjust that pH somewhere in the range of 3 to 5. Typically, if it's a low pH, which you're seeing when you're derouging, it's not going to be as much of an interference as a high pH. These can be adjusted with just an acid that you have, that you're using your derouging with, or if it's too low, with a sodium hydroxide solution. What you're going to do is then take that solution and you're going to add the contents of one of the reagent powder pillows that are with the kit into the vial. You're going to just put the cap on and invert to mix a couple times. What you're going to immediately see, if there is iron present, is a orange solution developing, which is good if you're derouging. You want to get that iron off the surface. You're going to wait 3 minutes, and you're going to, at the same time, go ahead and fill a second vial with the blank solution and zero the instrument. And then you're going to come back and read your iron. If that iron is increasing over time, you are still removing the iron, but if it plateaus off, then you've hit that plateau and either can consider, depending on where you're at in your derouging process, stopping or increasing your acid. You typically want to read these samples pretty much after you take them. You don't want to store these for later analysis the next day. So then sometimes numbers obviously are a little too high and you might have to dilute the solution. Then you would just multiply that result by the appropriate dilution factor. And these are all can be read either on the actual colorimeter that you see here in the picture, which would be typically read at 520 nanometers, or on a spectrophotometer, which you could then read on at 510 nanometers.
Great, thank you. So why would you establish a routine cycle or a maintenance cycle versus these extended or very long high temp, high concentration, possibly using nitric acid derouging cycles? You want to have prevention versus reaction. It's always better to build something into your schedule than have something be a surprise and then it happens. Of course, we all know that this always happens at 3 or 4 o'clock on a Friday afternoon and you can't use the tank and then everybody's scrambling. So you want to be preventative rather than reactionary. What the routine maintenance would do is remove the buildup of that non-visible rouge and just keep your tanks in that nice, shiny, brand new state for the lifetime of that vessel. Now, if you're in a buffer prep situation, and maybe, we all know that if you're using a glucose or a salt solution, they all go in the solution. They're all readily cleaned with water fairly easily, but you also have those, extrinsic factors that you might not consider, like your slip agents, your olamides, your ceramides, that could build up on the surface. You might have actual buildup of residue that maybe wasn't caught during your cleaning validation. So if you just incorporate a routine maintenance, a cleaning and derouging cycle, and you could base it on the frequency of some sort of PM, you could eliminate that reaction, bringing the tank out of service and having to deal with it in an emergency. If you do have rouge buildup, if you use the cleaning chemical, so if you already have an acid step in your normal cleaning process and you do have an event, you can use the normal cleaning chemical from the acid step of the routine cleaning cycle and what this does is you already have your limits. They've already been calculated. You already went through the exercise. You don't have another chemical to try to bring into the system, have QA release, have EH&S approve, and go through all the red tape that is required to bring in a chemical in-house. And these are these are very typically pre-rinsing detergents, so they also will remove any of the other process residues that may be on your tank. And this frequency will be based on your cleaning validation, cycle design, and of course your buffer materials, your contact times, your dirty hold times, as we showed in that other slide previously with the buffer tanks, that they determined their dirty hold times and their process hold time and their actual batch hold times. Now we have some case studies to show you what we actually have encountered, and Amanda's going to walk you through some of these because she's done the work.
As you can see in the first pipe sample here, it's an untreated piece of pipe that was cut by our maintenance department, and then we would go into a cleaning prior to our derouging step. In the second sample, you see it was with a citric acid detergent at 30%. At 70 degrees for 5 hours, and you're getting back that shiny silver surface that you're really hoping for. And the same with the second one, you have your phosphoric citric acid detergent at only 20% at 70 degrees for 3 hours. So with all of these, you want that temperature, you want that time, and you want that concentration to remove that rouge, which is fairly dark in the first sample.
The other thing to remember with actual piping is you want to make sure that you get an adequate flow rate, so you actually get that turbulent flow through these pipes, so you can remove that rouge with the action of that turbulent flow.
In this second case study, we did another pipe sample, and what you would start with was, again, your formulated, well, in this case, your formulated alkaline detergent, but any cleaning procedure that you have in place for an hour, 80 degrees, and you still see that yellow residue. So what that's telling you is that you're probably dealing with a type of rouge. Sometimes you might go through these procedures and find that your cleaning procedures are, then it probably was not a rouge sample. So then after the sample was cleaned, they went on to a phosphoric citric acid based detergent, and again at about 20%. And the good thing about a lab study, as you can see here, you can take out that piece, look at it really well after an hour, 2 hours, 3 hours, to determine when you actually have reached what would be a visual clean for your facility. So after that 1 hour, you see that reddish yellow. After 2 hours, you get a metallic silver, but then after 3 hours, you're seeing that bright metallic silver, knowing you've probably reached the end point of that pipe cleaning and derouging.
And when you do it small scale in the lab like this, then you can take that to your actual process equipment, and then you're not really experimenting at that point. You actually have a process that you can transfer at scale.
This next case study was actually done at a facility, and there we did laboratory tests for them prior to the actual derouging here. And we came up with cleaning with a 5% alkaline cleaner for 2 hours at 60 degrees, just something to make sure you're removing everything that you can. And they came back with a then 25% phosphoric citric acid-based cleaner that they recirculated in this vessel for about 9.5 hours at 70 to 80 degrees C. And as you can see, it's a very big difference in what their visual endpoint is.
And then in this study, it was an autoclave that they had some rouging you can see around the welds and around the bolts. And what they did here is they actually used our acidic cleaner and went in and sprayed the surfaces and then went in and manually scrubbed it. So it didn't take the 4 hours to do this, but there's a picture of it after how it looked. So here's an example of how to kind of shine up your autoclaves using acidic detergent. There's another picture on the next slide. We have, you see that kind of a rainbow effect that can happen with some heat. And then after, the metal looks nice, bright and shiny again after your treatment of your 15% acid detergent solution with a manual scrub. And then here's another example of a steam trap. So this is typical rouging that you might see. So we have our untreated steam trap, one that was treated at 15% CIP 200 at 60 degrees for 4 hours. And then, again, to determine those experimental conditions that will work when you actually go out on the floor, you have your 20% CIP 200 at 80 degrees for 4 hours. So it actually took an increase in temperature. So this is a nice example of how you can play around with the percents, you know, by bumping up that percent by 5% and by bumping up that degree by 20 degrees. You can see where you have a nice, bright, shiny metal on that third picture, but in the middle picture it just wasn't adequate. It just wasn't enough. So this is just a slide of some of our acidic cleaners that we've been talking about throughout the presentation. So we have our CIP 200 acidic cleaner that it's great for removing those inorganic soils. It's really our workhorse. It's excellent for rouge removal. It's a phosphoric acid citric acid blend, and this is usually my go-to product. Our ProCleanse 2 high performance acid cleaner, it's phosphate free, it has an analyzable surfactant. It's great for rouge removal. It's a citric oxalic blend, and it's definitely effective for passivation, and it does comply with ASTM A967. And then we have our CIP 220, which is our hydroxyacetic acid based detergent. It's phosphate free, and this is actually a really good routine cleaner and passivator.
All right, thank you, Beth and Amanda. So before I start addressing some of the questions that have come in, and I've seen a lot of great questions come in, just to kind of summarize what Beth and Amanda were talking about is some of the important aspects of the really robust rouge and I guess stainless steel maintenance program. You know, the first key step in it is going to be a thorough cleaning with an alkaline detergent. So what this does is it helps remove any organic residues. So any kind of residue that would prevent the acid from coming in contact with that surface to really facilitate the derouging process or the passivation process. And we usually follow that up with you know, a higher concentration, high temperature you know, application of an acid-based product. Again, we're talking, I think Beth mentioned tact, so you're looking at time, action, chemistry, and concentration, and temperature. And by, you know, kind of adjusting how those different variables interact, you can optimize your derouging and passivation procedure. Okay, so with that all being said, I'm going to just start with some of the questions that we've received, and we'll get to as many as we can. And as Amanda Biddlestone said at the onset, anything that we can't answer right now, we will be happy to answer offline through email. So the first question that we had, and this was during the kind of the explanation of what rouge is and where it occurs, was, does rouge ever occur on aluminum?
Yes, you can get rouge on aluminum. You can especially get the type 1 rouge that can be transferred from one surface, maybe downstream in a pump or in or you know, on an impeller, and it can be transferred to that aluminum, or it can actually happen. That would be the best case that I would see, or you would see some discoloration of that metal. But sure, you can get it on aluminum, especially when you have that is kind of like the what the sacrificial rouge spot on a naval vessel. Don't they always put like a sacrificial bolt? So yeah, that can actually cause rouge right around it with that non-compatible metal.
Right. And I think the biggest difference when you're talking about aluminum versus stainless steel is going to be that remediation strategy, and that with stainless you're going to use a high concentration, high temperature acid, and I'm not, and Beth, correct me if I'm wrong, but I don't think that would be your approach with aluminum.
No, I would probably look into replacing the part.
Yeah. All right, the next question came about during the discussion of the different types of rouge. The question states, if type 3 rouge can be powdery, shouldn't we be worried or concerned that water for injection or steam will be contaminated with these powder particles?
Yes. Some people actually implement systems like they analyze or they pull samples and they're looking for either free iron or are they examined by ICP in like actual in the process stream itself. But yes, but what you can do is you can do the same type of cleaning and derouging to remove that powdery, you know, magnetite layer. So you can clean it and get at that powdery surface off of that. But you can, if it's a water system, you can put systems in place. We've had some customers do that.
Yeah, and then Beth, to build on that answer, with other, I guess, occurrences of type 3 rouge, now not where you'd see this powdery type 3 rouge, but more of the kind of glossy-looking black rouge, it's almost more risk-averse to not attempt to remove that, because attempts to remove that magnetite, that black type 3 rouge layer, can sometimes lead to just certain areas of it sloughing off and getting into your water system or into your steam supply. Moving on to the next question. This has to do with, I think, stainless steel characteristics. The attendee asks, if I swap my 316L with duplex or super duplex steel, will it help to minimize buildup of rouge, specifically class 2 or class 3?
I would have to look up what super duplex steel is composed of,
okay,
based on the actual, you know, how much iron is in it, how much molybdenum, how much nickel. There's certain calculations that you can do. It's actually called I use it as a preen number, and it actually gives you a calculation that you can look at your percent carbon, your percent nickel, your percent molybdenum, and actually come up with a quantifiable number and rate it. And then what I would do is compare it to the preen number of 304 or 316 stainless steel. But I'm not familiar with that one. I'd have to look it up and get back to you on what the composition is.
Okay, that's one that we can address more in depth offline. Next question, excuse me, is just where can one get the references that were mentioned earlier, for instance, the ASTM A380. I know that if you reach out to these organizations, you can actually get them from their websites.
Yes,
so ASTM or ASME, they're all available there, as well as through some third-party, I guess, resellers. Just one note on those is there's typically pretty modest costs involved with those, but yeah, they are all available from the organizations themselves. The next question, how would an individual know a surface is clean enough to begin passivation? I think this is a great question. It kind of speaks to that kind of industry age-old question, how clean is clean? My recommendation, and Beth, you can feel free to build on this, my recommendation would be to approach this as you would cleaning of a product contact surface. So you're going to take into account potential risk from residues that could be left on the surface. What we're really trying to go after here is any kind of gross organic soils or residues that would be left on the surface that would prevent the acid from coming in contact with the surface and really doing its job in removing rouge or reestablishing that passive layer. Did you want to add to that?
Yeah, you could look, there's different methodologies. Like you said, if it's a new piece of equipment, that's a little bit different. If you're trying to remove those cutting oils or lubricants, then I would just recommend a general cleaning. But if it's an actual process soil, you can do coupon studies to determine what is actually clean by looking at visibly clean, water break free, and gravimetric analysis of that, or even take it up to HPLC or TOC, just like you would a normal process soil.
Okay. We have a couple questions around the COSLO test kit or the COSLO meter. So the first one is, with this, in regards to the COSLO test, will it work on a curved surface, for example, a tank wall?
It depends on how curved the surface is. You do need a small, I would say about a centimeter of flat surface where the actual nib can come in contact with that surface. It doesn't have to be a large surface area, so we have done it on our tanks here, and it works fine.
Great. And this is another one regarding the COSLO meter, and this one we may have to do a little bit additional research on. The question is, what research is referenced for the passive range of the COSLO meter, i.e. the -200 to -400 millivolts?
It's discussed in the, well, let me look up in the actual ASME if they give the range in that document. If you give me a moment, or we can take it offline. And
Yeah, I think we'll address this one offline. I think it's a great question, and I think we have some additional information around it.
Mm-hmm.
There was an additional question regarding the passive layer and passive, specifically the case study you talked about with the passive layer and buffer preparation tanks.
Mm-hmm.
The question was, what about bioreactors running for 10 to 15 days? I think my answer to that would be, this is going to vary. There's a lot of variables at play when you're talking about the impact on the passive layer. So what we saw in this case study may or may not be representative of what this individual would be seeing in their bioreactor. You're talking about different raw materials and different operating conditions. So it's tough to speculate on how long that passive layer would remain without really having a better understanding of the process that's taking place in that bioreactor.
Yeah, in this specific case study, it was a high salt solution, so that is just notoriously, it is just notorious for pitting and corrosion. So in a bioreactor, I would expect less impact because you normally have a little bit more of a buffered, from your protein solutions, and it's a little bit more of a buffered solution and a buffered process residue. But yeah, it is something to look at.
All right, great. The next question, one of the attendees asked, could either of us please detail what is meant by high temperature or high temperature steam? I think just look for more specifics around that. And the phrase that improper welding can cause or provoke rouging.
Well, first of all, I get to your steam. It's just normal and whatever you would sip with, so your 121 degree steam would cause that black. And like I said, we typically saw it in our SIP systems. What was the
and I'm sorry, the follow-up question was regarding welding and what is meant by improper welding and how that can lend itself to rouge formation or corrosion.
So improper welding, what I would say is just a surface that has not been properly cleaned before it's welded and then passivated after, cleaned and passivated after it's welded. And typically, in your lower carbon, like your 316L, it's not something that you have to worry about because it specifically has a low C component to it. So it would, I would say that, in your 316L, it's not really going to be that much of an issue because it's really that precipitation of those chromium carbides that cause that, caused by that high temperature and welding that'll cause that. It can also cause, if it's, the little micro pitting and the stress cracks can happen around those surfaces. So I would say improper welding is not really the improper welding, it's the improper cleaning and post-cleaning and passivation after that weld.
All right, great. Thanks, Beth. The next question was when we were going through some of the, I guess, derouging characteristics of a formulated product versus a commodity acid. One of the attendees asked that he's seen the data for 15% CIP200 relative to 17% nitric acid. Mm-hmm. What is the comparison for a typical CIP200 concentration used for nominal cleanings? I'm assuming that would mean what we typically recommend for CIP200 in a cleaning application being 1 to 5%.
Yeah, typically your acid concentration could be, I typically recommend about a half of whatever your alkaline detergent cleaning is. So it can be, like 1 to 4% at, I would use a higher temperature, so 60 to 80 degrees C for 10 to 30 minutes. That's a typical acid stainless steel routine cycle. The thing to remember with that acid, it's what you want to do with your tank, and when you have your rinse cycle as well, you always want to make sure you rinse with that higher temperature of water so you get that dry surface quickly too, because that actually helps. The quicker it's dried, the quicker it's exposed to oxygen, so that comes into play too.
Yeah, and one thing I would add to that is I think this speaks to what Beth and Amanda spoke on about prevention versus remediation. And what we're looking at in some of these case studies and in some of the graphs where we kind of looked at the different characteristics, the erosion characteristics, was looking at a fairly serious rouge issue. So that's why we look at, a 15 to 20% CIP 200 concentration. If you're looking to really just maintain the stainless steel surface, then yeah, just as Beth said, typically 1 to 5%, for maybe 30 minutes, depending on what you're cleaning and the status of the equipment. Another question regarding the different derouging or passivation characteristics is that we have mentioned that nitric passivation reduces the thickness of the oxide layer. Is that the same issue with citric acid? And there are a few follow-up questions. I'll let you guys address this first one.
Not so with citric. It would actually just dissolve that iron, and since it would bind up that iron, it would go into solution and remove it that way. With nitric, it's just going to keep it, since it's a mineral acid, it's just going to keep dissolving whatever metal it has. Okay, the follow-up question would be, what are the claims around CIP 200? Being phosphoric and citric acid blend. I'm not quite sure. I'd probably have to take that offline, and because I'm not sure. I need a little bit more details on what the person's asking. Okay, and then the last part of the question is: does it matter that the oxide thickness is reduced, since one of the key components is the increased chromium to iron ratio? The oxide isn't really reduced. You're just removing that iron from the outside surface and exposing that, so the chromium is more the chromium is in more of an amount, and then the actual exposure to the oxygen would cause that chromium oxide reaction. But I'm not sure. I think that was my understanding of it as well. It's another one we can follow up with the attorney that's asking the question and address that one offline. Okay, let me move to the next question. This individual is asking that they are dealing with a process that only uses caustic in the CIP cycle, i.e. no acid. Would adding an acid cycle to the CIP help maintain rouge levels, or I guess prevent rouge? Yeah, I was like, not maintain. It would actually prevent. And absolutely. You'd also get a little bit of benefit with your rinsing attributes too of your total cleaning process. And that's not to say that you'd have to do it every cycle, but maybe you could look at your frequencies and incorporate it into some sort of cycle. So maybe after maybe monthly or weekly, depending on how often you're running that cleaning process, and incorporate it at least periodically. But yes, I generally recommend it's a twofold approach. You want your alkaline cleaner followed by your acidic cleaner, and it's kind of like using the jet dry in the dishwasher. Yeah. All right. The next question is again. It's going to be the different states of rouge or different rouge types. Mm-hmm. And the question is there a way to qualify, the various rouging states or statuses? So how would you determine your derouging actions? Is there a way to monitor, the not visible rouge? Well, other than the HOC, which would look at it, using a certain wavelength, that would be the way I would approach it. But if it's, if it's not visible and you have some sort of routine maintenance, that's the state you want to keep it at. But once it's visible, what some people do is they actually assign a percentage to that, amount that could be in the tank, and so they say anything greater than, it's visibly clean. However, we're seeing some corrosion, so anything over maybe what we assess in a subjective assessment of 20%, that's when we do something. So I don't know if that answered the question. But yeah, I mean, if not, I'm sure we can follow up after the webinar. Another question that I can address is a question around the percentages of CIP 100 and 200 used in the case studies.
yes. The question was, are they consider? Are we basing those on the I guess bulk CIP 100, CIP 200 products? And the answer to that is yes. So when we're talking about using 15 to 20% CIP 200, that's not relative to the acids present in the solution. It's to the complete formulation itself. Okay. Next question is, will a daily acid wash with a 1% citric acid prevent rouge formation in vessels that are steamed in place?
Oh, based on my experience, I'm going to answer no. Because steam in place, again, you have that. Is it a piece of clean equipment that you're bringing in and you're steaming it in place, and that's what you're doing? And just using citric acid, I mean, it depends, but it's been my experience, no, that's not enough. That's not enough. And in some cases, it may not, no amount may be enough. You may just have that black layer, that that passive layer, that if it becomes a problem, you may have to have it electropolished. So unfortunately, it depends on how much is there and where you're seeing it.
Okay. The next question is, can you recommend an alkaline cleaner for stainless steel? I can address that. Well, the short answer would be yes, but the longer answer would be I can't give you a recommendation now. It's going to be based on what you're trying to clean from that stainless steel surface. And really, depending on what you're cleaning, an alkaline may or may not be the best option or the best route to go to. I mean, typically, if it's anything organic, then yes, an alkaline cleaner would be the way to go. But if you're looking at inorganics, any kind of maybe metal compounds or complexes, then it might take something of different chemistry. But that's something you can contact Beth or Amanda or myself offline, and we can kind of delve more into it to really develop a better recommendation. Let's see, next question would be, if you mechanically remove rouge, will that result in damaging the steel and then result in future rouging?
It really depends on the type of rouge. If it's type 1 and you go in there and by mechanical removal you're using a nylon brush and you're just going in, or with some sort of whatever you use to clean in your normal cleaning procedures, then no. Like for example, that autoclave, they went in there and used mechanical action. So I'm not talking using sandpaper or green scrubby pads or Brillo pads. We're not cleaning that. We're not cleaning that way, and don't clean that way. It's one of my pet peeves. But if you're going in there and you're just using the mechanical action to provide some, again, it goes with those parameters of your time and your action and your concentration and your temperature. It plays one of those roles in the parameters. So no, if you're going in there with a Brillo pad trying to scrub off type 2 rouge, then yes.
Okay. Next question is, have we looked at the optimal passivation conditions that could maximize the time between, I guess, repassivations? And have we looked at maybe a way to extend the effectiveness of a passivation so we don't have to do it so often?
Yeah, I mean, passivation occurs naturally, so as long as you're cleaning appropriately, you're going to build that passive surface naturally. But if you're doing something to impact that passive surface, it really depends on your frequency of operations, and it depends on how routinely you're cleaning and passivating. There's a lot that plays a part into that. But yeah, you can determine, like we showed with the buffer tanks, that they actually did determine a time. So yes, you can, but there's a lot of things that play a part of that. Do you want to add on?
No, I think you hit it right on the head, in that it's very similar to cleaning, in that it's really going to be dependent on what's going on in that particular vessel as far as the effect of, I guess, the effective time that that passive layer remains passive. So if you're doing a process where you have a lot of chlorides or other, halides in the tank, then it's going to deplete that passive layer faster than, if you're using an solvent or something like that. So unfortunately, it's going to be one of those answers where we have to say it depends, because there's a lot of variables at play on that one. A question came up about type 3 rouge. How can you remove type 3 rouge, and is CIP 200 effective in type 3 removal? Let's say, for example, a water still. I can address half of that, and Beth, I'll ask your expert opinion on the other part. CIP 200 is not typically recommended for rouge, type 3 rouge removal from water systems. That's not to say that it will never be effective, you won't have success with it, but in most of the type 3 rouge that I have encountered, you need something either much more aggressive in terms of a chemistry, or you need to mechanically or electropolish that surface to really remove that rouge layer.
Yeah, I mean, at that point you're talking electropolishing or pickling or just accepting it.
Another question is, the derouging process synonymous with CIP procedures, or is derouging an additional cleaning step? I know how I've approached this in the past, and that has been that derouging and rouge removal usually fell under the umbrella of maintenance. So in tank maintenance or equipment maintenance, the cleaning, typically the cleaning validation master plan or your cleaning validation scope would just apply to cleaning product contact surfaces and cleaning process-related residues from that surface. I normally see the derouging process as the maintenance step, whether it's done monthly, weekly, quarterly, however you choose to approach it, but it's a maintenance step, not necessarily part of the cleaning.
That's absolutely right. You can incorporate it into the cleaning step, of course, but it really depends.
All right, we're getting down to the last few questions. Would you expect that a 316L stainless steel surface damaged by chemical etching could be remediated via a derouging process or CIP process with maybe one of the acids that we had described?
No, and unfortunately, no. At that time, you're looking at either, some sort of mechanical polishing or electropolishing. Once you get a tank that's etched, or some people, they just accept that it can be etched, and then they incorporate proper cleaning and derouging, procedures on an actual routine basis, so they don't have the buildup of the residues and the rouge in those, in those little micro pit, those micro valleys and peaks. But generally, no, you're not going to be able to use an acid to fix that.
Okay. Last question is again regarding CIP. Some of the CIP products is we mentioned that 316L stainless, the passive layer can be maintained with normal use of CIP 200 or Propylens 2. The question was, do we have data that would support this in terms of like COSLA readings or a piece of technical literature? Personally, I know that we have case histories where that we've looked at this, but I'm curious from you guys' perspective, is there additional technical literature that would address this?
We have some technical tips, but I don't believe we actually put the data out there. As far as like the data that we showed in the presentation, it's not out there as far as something that we shared. But we do have technical tips regarding procedures for derouging and passivation. What is derouging? So that, we do have literature, but not necessarily the case studies that maybe this person is looking for. But I'd be happy to talk to them and we could discuss it.
Great. Well, that kind of addresses all the questions that we received throughout the webinar and a few additional ones afterwards. So before I turn it back to Amanda Biddlestone to kind of wrap up, on behalf of Beth and Amanda Deal and myself, thank you everybody for attending. Thanks for the great questions. And if you have follow-up questions, you'll see Beth and Amanda's contact information on this last slide. Feel free to reach out to us. You know, we pride ourselves on being a resource for you and your processes and to help you guys as much as possible. So with that being said, thanks again, and turn it back to Amanda.
Thanks, Mike and Beth and Amanda. Thank you all for attending our webinar today. We appreciate you taking the time to learn with us and hope you found this session beneficial. And thanks again. This concludes today's webinar.